merci. Merci. Thank you very much, Isabelle, for this nice introduction. The first thing I would like to do is to thank the whole CIRMMT team for the invitation. I'm very honored to be here. I'm very happy, and it's always very exciting to be in CIRMMT because there's a lot of stimulating discussions and things all over the place. So, well, to introduce my talk today, I would like to start with a little kind of personal history of musical acoustics. Say that for many years, acousticians have been known to analyze the sound spectra. And, well, it's an old habit coming from Mr. Fourier, just weighting the different frequency components. And it took quite a number of years to realize that the spectra was important, but what was more important was probably the time evolution of the spectra. So I think the idea came mostly from researches on speech, and the machine here, the K sonograph, was the first one to analyze the time evolution of the spectra. So at that point, I would say musical acoustics was looking like that, because the next step was to try and find relations between what we could analyze in the signal, in the sound signal, and what were the elements in the instrument. So that's the beginning of studies on the physics of the instrument, not the beginning, but the great time for the development of studies on the physics, the modeling, the physical modeling of musical instruments, trying to understand where the different things we could observe in the sound were coming from in the instrument. It was also the time for the development of work on the perception of musical sound. So, well, that was probably something around the 80s, the great time of the physics of musical instruments. And now it took a few years for acousticians to realize that instruments by itself just does not sound. You need a player. So the player was the missing link. I mean, the control of the player on the instrument was the missing link between, let's say, the physics, the instrument making, and the music. So that was something like 20 years ago when studies on the control of the instruments started to grow in the musical acoustics community. So at that point, the picture looked like something like that. We have introduced now a player. We also have a listener, and of course the player himself is a listener, so you can think of that as a looped feedback system. And, well, the sound obviously also has to include, the sound analysis also have to include the room acoustical properties. And, well, there we are. Now we have a nice player playing a nice, very nice instrument. He's playing the instrument in a wonderful spot. Well, everybody recognize Andrés Segovia. He looks happy, doesn't he? And at that point, we realized that it's also, and I think that's what we're doing now, realizing that we also have to take into account the musical context. So that I think that today the picture looks a bit like something like that. We have still the instrument, the sound, all the previous parameters, and then we have to put that in a musical and cultural context in order to study that. That's a short summary of this quite personal, I should agree, history of musical acoustics, and I'm going to focus on the three steps here about the instrument, studies on the physics of the instrument, the control, and also the musical context. There we are. We have a very nice player. He plays well. Actually, the pictures do not correspond. But this is a maker, a flute maker, making a very nice instrument. He's playing a very nice music. You can recognize here, and here we got the sound. So to try and explore the relations between all these parameters, I'm going to structure or organize my talk in three main parts. The first part is going to be about the instrument. The second part is going to be about the player, and the third about the maker. Well, as you said, Isabelle, I'm going to focus mostly on flutes, but well, at some point we may have a little of piano, just for a change. Okay, so the instrument. The question is, what does the physics of the instrument tell us about the required control? I mean, if we know enough of the physics of the instrument, this should tell us how the player should control the instrument. So let's start by the basic things about the physics of, well, a flute. For instance, we all know the open resonator resonances with a half wavelength, one full wavelength, one and a half, that are giving the different resonances of the flute or any wind or woodwind instrument. We also have to take into account the side holes. Here we have two different flutes. This is the 19th century, actually it's a copy of a 19th century traverso with very small side holes here. And as compared to that, we have a modern Böhm flute with much wider tone holes here. A very familiar way for acousticians to describe the acoustical properties of the resonator is to discuss or to analyze the input admittance, which is actually the response of the resonator as function of frequency. If you look at this input admittance here, you can see the different resonances that correspond to the maxima, different maxima here of this input admittance. We now have a good description, good modeling of the different elements, so that this input admittance can be measured or calculated. And of course, for a woodwind instrument, you have different fingerings, and each of these fingerings give a new admittance. And on each of these admittance, you can find the different resonances of the instrument. Well, just to illustrate that, let's have a look at the 18th century traverso, which looks like a flute with a cylindrical head joint here. It has then a conical body, and well, the end here generally, well, changes a lot on from different makers, but generally it opens a bit. It has these 7 side holes with very small diameter, and if you put all the geometrical information about the instrument in the computer, you can calculate the different resonances, and this is how it comes out when you look at the frequencies of the different resonances when you study the different fingerings corresponding to a chromatic scale. So, as expected, when you play a chromatic scales or the fingerings of a chromatic scale, the first resonance is going to follow nicely the expected law. But if you now look at the second and third resonances, you see that, well, maybe for the 2 first notes here, they follow the same expected relation, but then when you move to the other notes, it becomes much more complicated. That means that it's mainly because of the small diameter of the sound holes, of the tone holes. We're talking now about inharmonicity. That's the good or bad harmonic relation between the different resonances of the instrument. Well, that's a bit technical, but it's just to show that the knowledge we have now on acoustics can be translated into a kind of summary of the acoustic properties of the resonator, which is, for most woodwind instruments, it's a very useful tool to study the intonation of the instrument. In the case of the flute, things are not so easy. We have forgotten one main actor here, that's the player. Because the player is completely changing the intonation of the instrument. So I'm going to try and illustrate that by playing, this is a modern Böhm flute, playing 2 scales using exactly the same fingerings. Well, it's almost one semitone apart. I don't know if the semitone was okay. Yeah, something like that. So that means the player has a very strong influence on the intonation of the instrument. But of course, the player that's because of the lips coming on the embouchure. But of course, the player does not put the lips on the embouchure just for intonation purposes. It's because he needs that to play the instrument. So we need to go a bit deeper in what the player is doing. So what's the control on the flute by a flute player? Mostly the lip geometry and the blowing velocity. That's the two main parameters. And I'm going to focus a bit on the jet length. These are this drawing of the two lips here. And the jet is directed towards the labium, which is here. And of course, moving the lips, the player can adjust this jet length. And this is actually one of the most important things when you play the flute. You have to adjust correctly this length and the blowing velocity. And to see how the player has to adjust those two parameters, we need to go a little further and see, well, let's go a bit deeper in the, well, let's say in the engine, or this is a recorder cut so that we can see the air windway. The player is pushing air in the windway so that there's a jet formed at the exit here, and the jet is directed to this sharp edge here, which I will call the labium. Of course, this is one open end of the resonator, so that's a place where we expect a lot of acoustic movement here. That means the jet is coming here in an area where there's a lot of transverse acoustic flow. We can have a look at that using, that's a high-speed camera. So the picture is, the movie is slowed down by something like 1,000, I don't remember exactly. And that's the very beginning of the transient. The jet is forming and directed towards the labium, and the interaction here from the jet with the labium is generating the acoustic energy that is going to accumulate in the resonator. When, well, we're talking about 1 or 2 milliseconds, and the whole movie here is probably 5 milliseconds or something like that. You see that while the resonator accumulates the acoustic energy, the jet starts to oscillate more and more, so that under stationary oscillation, you see that the jet is going from one side to the other side of the labium. And what the player has to do is to make sure that this happens correctly, I mean with the correct phase. And that means the player has to adjust the hydrodynamic wavelength that is here between the flue exit and the labium. So in a way, what the player has to do is just to tune parameters so that we have this correct ratio here. And well, obviously the player has the two parameters. When we play a flute, when you play a recorder, the jet length is given by the flute maker, so the player doesn't have any influence on that parameter here. And of course, the player needs to adjust that to the pitch he wants to play on the instrument. Well, this one is going to be just a bit technical, but I'm going to use an indicator of what the player is doing, which is a dimensionless jet velocity. It's just the ratio of the jet velocity compared to the velocity that would be needed to reach the labium in one sound period. Well, for those who are familiar with fluid dynamics, it's the inverse of a Struwell number. Let's consider that as a kind of RPM indicator of what's happening in the engine of the flute. This dimensionless jet velocity is going to be between, let's say, 7 and 14, independently of the regime you're playing. For instance, if you take a recorder and blow very softly and then increase progressively the jet velocity by blowing harder and harder, you will start by playing the first regime here, and at some point switch to the second, and then switch to the third, and back. If you plot that in terms of this dimensionless jet velocity, you see that jet dimensionless velocity starts something, well, let's say 4, 5, 7 here in this area, and reaching something around 14, switch to the second register. Since the frequency is twice the frequency of the first regime, dimensionless velocity is divided by a factor 2, and so on. Now, these are nice drawings. What happens in a real instrument? This is a measurement on an actual recorder, and well, as you can see, the intonation is strongly dependent on the jet velocity. What you can see here is 1 octave, and you can see that blowing on the first regime here with very slow jet velocities, you can play almost 1 octave lower than the first resonance of the pipe. So here again, the player has a very strong influence on the intonation. So to try and summarize these different effects, I'm going to talk about, well, let's say little additional tubes that we would plug onto the instrument. And blowing softly is equivalent to having a rather long correction here, a long tube, while if you blow much harder, it's the equivalent to having a short tube. And we also have the same thing about the position of the lips, because if you have the lips far away from the labium here, the blowing hole is quite open, and this corresponds to a short tube, while when you push the lips forwards, this corresponds to a much longer tube. I'm going to use those small tubes as an image of what the player is doing when he's playing. He's adjusting the length of a small tube so that he gets the right intonation, the intonation he wants to get. Well, just to illustrate a bit this thing, we had some years ago measurements on 15 flute players from an international selection. We had people from all over the world, and they have different strategies, like the position of the lips and the blowing velocity and things like that. But when you plot that in terms of dimensionless velocity, you realize that as functions of the pitch here, they all have the same dimensionless velocity. So I would say that's the basic thing you need to do if you want to play a note on the flute. That's why it's not so obvious for when you take a flute to just produce a sound. It takes a few weeks or months, I don't remember, to learn and do that at the beginning. You have to adjust those two parameters. But then you've got the sound, but of course the player wants to do more than just producing a sound. He wants to make music. So let's move to the second part of the talk, which is about the player. So the question is, what does the player do on top of this basic control to produce music? And the related question is, can we find any evidence of musical intention in this control? Well, to introduce that, let's move to, well, that's a composition of mine. Yeah, where you have just trying to understand how different players would organize things. And we have 4 different players here from this international selection we had. And, well, they're playing the 4 bars up there. And you can see very different strategies. Of course, what is plotted here is the pressure measured in the mouth of the player. And of course, you can see the vibrato here as very wide variations in the blowing pressure. This player is obviously making something quite different, and so on. You can also see very different strategies on the way to just to play a note. Player 2 and 3 here, they have a small start and then they go, while player number 1 and number 4, they just go direct. So there are very different strategies here. And the question is, are they different strategies because they have different ways of playing? Or do they have different strategies because, well, obviously it's not music? they're just being nice to me. I ask them to do that, they play those notes, but it doesn't have any musical sense or any musical meaning. So I move, next step, I move to music. And we compare here two players. That's the mouth pressure. Next plot is the distance from the lips to the labium. And you can see that they behave quite differently, because player blue on the left is almost constant jet length, while player green is moving quite a lot. In terms of dimensionless velocity, it's also quite different. So I try to analyze this a bit more, well, just focus on the three first notes here. And my idea was that the player was giving a shape, a time shape to each of these notes, and the time shapes was the basic thing to structure the music. So we thought of having three numbers to describe each note. So that's the dimensionless velocity, that's the three notes from the previous slide. And well, one thing is obviously the mean value of the dimensionless velocity. Second thing is it decreasing, like kind of small diminuendo or something like that, or is it increasing? And third thing is that are there lots of oscillations around this? Well, obviously it's the idea of the vibrato or something like that that comes here. So this is the mean value of dimensionless velocity here. Well, there seems to be some kind of common way to do things. It's much more obvious when you look at the direction of each note. This could be positive or negative depending on diminuendo, if it's a diminuendo or crescendo. Well, diminuendo or crescendo are obviously not the right words, because it's a musical term and it's not what happens here. It's just the shape of individual notes. And of course, there's something very strong appearing, which is common to all three players here, between numbers, the sixth note and seventh note. And of course, this corresponds to the first part of the little tune and the second part of the little tune. And okay, let me play for you the example. So this is player blue. Player green. And Mr. Red. No. Well, in a way, I realized I made a terrible mistake here. Because I chose this tune because I thought, well, it's probably the easiest tune you can learn, what French kids learn when they start to learn to play a flute or other instruments. And, well, I did not realize that half of the players coming for the measurements did not know that tune. It's a French tune. I don't know how many of you know it. Okay. I didn't realize that it was only a French tune. That means that the differences we have, as you could hear, are probably also coming from the fact that they don't have the same idea of what this music is. That means that the tone is, and the control is an element of a musical performance. It's not just producing a sound, it's trying to make music with it. And tells us that before trying to analyze anything, we have to make sure that we know exactly what the player has in mind, what the player is doing. So I'm going to try and illustrate that by a little detour. What is detour in English? Okay, thank you. presenting a short study we did on the piano. We want to study the control of on the piano, and we first want to define a framework that's going to be efficient for this study. And to define this framework, we need to define the composition style we're going to be working on, the playing induction, and also the interpretative style. So what does that mean? The composition style, well, we have to make sure that, of course, all the players are going to know this musical style. So we choose something which is probably familiar to most of the players, and actually it was familiar to all the players we had. That's the Nocturne from Chopin. But we had to choose a piece of music that nobody knows. I mean, none of the pianists knew. And we had to make sure that there was no available recording of that, so that they wouldn't get inspired by any kind of recording. That's quite tricky to find. But we ended by Nocturne by Friedrich Kalkbrenner, who is very, very close in the style of Chopin. And I'm going to focus a bit more on the interpretative style and show two possible interpretation or two possible interpretative style here. First one is what I will say the classical style. I'm going to go a bit in more details here. Classical style is what I use to describe what students coming out of our main conservatoire in Paris, the way they would play it. Of course, they have the feeling of time continuity between the time of Chopin and now, so that, well, they know how to play this music, and they know that by kind of oral transmission. And opposite to that, we have what I call the historically informed style, where the players are referring not to the way you've learned from your teacher, who has learned from his teacher, and so on, but from writings. So just referring to writings and other historical elements. And if you look at those two things, it's very contrasted, because the classical piano studies insist on different things, such as regularity in the accompaniment. When you have triplets, you have to have the three notes regular, and so on. Another important thing is the good synchronization between the accompaniment and the melody. That means you have to play both hands together. Well, if you look at what's written in the text from that time, the text on the Nocturne emphasized the reference to singing. And there's a lot of emphasis on the fact that you should find a way to avoid the kind of harshness coming from the percussion in the piano. And to do that, you have to overlap the different notes. You don't, well, you keep the fingers on the keyboard. You don't end the note at the time you play the next one. And also the rubato is very important. Rubato being different from a gogic. A gogic is the variation of the global tempo, and rubato is the synchronization between the accompaniment and the melody. And the text emphasized the fact that singers are not expected to play on the beat or to sing on the beat. You play whenever you want, but in an expressive way. So we had tried to contrast those two different styles, and we used information coming from a grand piano with MIDI sensors. And the three things we're gonna look here is first the dynamics, so that's the velocity, the key velocity. And here you have in dark the left hand, that's the accompaniment, while here is the melody. What we have here is the synchronization between the two hands. That's the time difference between the notes whenever they are notes together, like here, for instance. And the last thing here is the instantaneous tempo, to see whether there are fluctuations inside one beat, one bar, and so on. So this is the classical style, and this is the historically informed style. As you can see, in the classical style, the accompaniment is played quite softly, so that the melody is played much louder just to make the melody appear clearly. In the historically informed style, the accompaniment is played much louder, and well, it's probably the same kind of loudness from accompaniment and melody. But in the historically informed style, you see that right hand, the melody may come very, very late as compared to the accompaniment. And last thing here, we're going to have a very regular accompaniment, while here we've got a lot of movement in the accompaniment, which is structured by bar by bar, or even beat by each beat. So let me play the classical style here. Nice. And next move to the historically informed style. Okay, as you could hear, the way to separate or to mix the accompaniment and the melody is completely different. They have a completely different conception of what a nocturne should be. So that means before studying anything on the control, I mean, all the differences we observe here are not coming from differences in the technique, they're coming from differences in the conception they have of the music. That means what the interpretative style is what you add on the reading of the score, the knowledge you had on that. Okay, so once we have clearly set and organized this framework, we can move to the next question and see and try to analyze the control. So here's a flute player whom I don't know, and well, I just took the picture on internet. I don't know what she's playing. But, well, obviously she's strongly engaged in showing some strong musical emotion here. So the next question is, can we find any evidence of the musical intention in the control? And to illustrate that, I'm going to present briefly a study we did quite recently with Isabelle here. These are measurements we did here in CIRMMT. And well, we have flute players playing the very well-known CIRMMT melody by Debussy. And that's the very first musical phrase here. And we'll get the pitch here so that we can follow the melody. Here is the mechanical power that is injected in the instrument. And now we have two things here to indicate the vibrato, because listening to the excerpt, I will play it after, you will realize that the vibrato is strongly correlated to specific musical intention in the playing. We here have the radiated sound power, and what we found was that each time there was a strong musical intention, as attested by the vibrato, the triggering of the vibrato here, it corresponds to a specific effort on the respiratory system. That means the musical intention was triggered each time by something special, like an effort on the respiratory system. And more than that, it was triggered by the lower part, the abdominal part of the respiratory system. Just check with Isabelle whether it's okay. Just maybe play that. So that each time there's this kind of musical intention, we found a strong correlation with some effort on the respiratory system. Comes the same at another, just a bit later in the music, so it's just a confirmation of what I said before. And we also looked at the sound spectra to see that also there was a strong correlation between things happening. I'm not going to detail that, there's lots of data here, but things like the evolution of the sound spectra was also strongly correlated to the muscular power. That means there's a specific muscular effort on the respiratory system that is supporting the melody. The player wants to show something. So how to try and interpret these things? Well, I don't have any real answer. That's the open question. What I find quite, there are some hypotheses that I find quite seducing. It's the player is it's to move from the player to the listener. What is the listener doing? And probably the listener is trying to find some kind of meaning in what he hears. And obviously, the listener is not listening, analyzing the spectra, the pitch, and everything like that. The player is just going into some kind of empathy with the listener is moving into some kind of empathy with the player. And well, I find the hypothesis of mirror neurons, which is quite seducing. I don't know exactly, I didn't work specifically on that, but it's just an idea. You know those neurons that are supposed to fire when you do something or when you see someone doing it. So people working in cognitive psychology consider that it's a way we have to understand the actions and the intentions of other people. So that probably could be a direction to try and see what is the listener doing. Does the listener feel really this kind of muscular effort on the respiratory system directly, more directly than the sound or something like that? Is it a way from the player to give some kind of emotion or shift the emotion of the listener? I don't have any answer. It's just ideas. We still have, I'm afraid, a lot of work for the future. No, I'm not afraid. I'm happy. Okay, no answers now. Huh? Let's move to the last part of the presentation about the maker. Going to try and summarize different elements that I presented in the design of a new instrument. What is the context here? The context is lots of orchestras now are playing on historical instruments. That is, they're trying to play on the instruments that were played at the time the music was written. And well, I showed two of these orchestras here, not here in France. And I must say this work we did last year, mostly Patricio, that was a team with Patricio de la Quadra, Camille Vautrin, and others. So for flutes from 18th century, I think there are no flutes from this time that are still in playable shape. So we have copies of those instruments, and well, I showed one on the pictures before. But for the 19th century, there still are some instruments that are played, but obviously they're getting old and probably a bit too old. So we're trying to design an instrument that would be somewhere in between the traverso I presented already and the modern Böhm flute. As compared to the traverso, the modern Böhm flute has a cylindrical body, very large side holes, and some kind of conical head joint here. But the transition from one to the other did not come at once. There were many people working on that. And, well, those people have been working on evolutions of the instrument. But probably the best known maker is Mr. Böhm. And we're going to focus on an instrument that he developed in 1832, which he called a new flute. That was a conical instrument, and as opposed to the modern cylindrical flute, he didn't have any patent on that instrument. So that there were many makers who made different models of this instrument. These transition flutes were built until the beginning of 20th century. So that's why we still have instruments that are something like 100 years old, still playing, but getting really old. So we don't want to make a copy, because there's not exactly one good instrument. There were many different versions of this instrument since there was no patent. And we're just trying to develop our own instrument here. And putting together the different elements we know on the instrument. So the idea is we try to predict the consequences of the maker's choice on the aesthetics, on the sounding aesthetics of the instrument. It starts from the bore geometry, and from the bore geometry we know that we can calculate the relative tuning of the instrument across the tessiture, and this is going to determine how the player has to put his lips. Does he have to push the lips forward a lot when moving to the high register or not? And this determines the blowing jet velocity. So if you take all this together, you can have a whole picture of how the instrument is going to sound. For example, if the geometry gives a tuning where the high pitches of the tessiture are going to be a bit too flat, the player is going to open, so he's going to have the lips very far away from the labium. And to keep the balance, this dimensionless jet velocity is going to blow very hard. So if you build a flute like that, you're going to have a very soft low register, and the more you go in the high register, the more sound you get. It's going to sound like crazy in the high register, or the opposite, depending on what you do. We also, so that's the sound evolution across the tessiture, which is a global indicator of how the instrument is going to sound. We also thought about the ease of playing, like, do we have to move a lot between different notes? That's the little tubes I added before. Is this tube kind of smoothly changing when you change from one note to the other, or do you have big variations? And of course, one important thing is also the spectral content, which is, we study the relative tuning of the different resonances, which I presented before as inharmonicity. Of course, we considered a kind of backward process, starting from here and moving up to there, defining a bore geometry. We started also by the observation of historical instruments. We had up to 8 instruments, and they have different bore geometries. Here are the bore diameter of the 8 historical instruments with this conical body. Sometimes the foot joint reopens, sometimes it does not. And the instruments have very different head joint diameter. That's a huge difference here. As compared to that, we have plotted here also the geometry of a modern Böhm flute to see that, well, it's quite far away. Here are the side holes, position, diameters, and so on. And as I showed before, we can translate these geometrical properties into intonation properties, or what the player is expected to do in terms of this this small tube. That's the imaginary tube that represents the adjustment the player is expected to do to play in tune. And what you see here is, if you look at this color here, the modern flute, you see that when you play on the first register, this tube gets bigger but very smoothly. If you look at another instrument like the gray one here, you see that it's not very smooth, because you increase it, and then you go down, and then you kiss very strongly up to here. So taking all these elements together, we designed bore, actually not one but two bores, which are presented here. The blue thing here is the historical instrument, and we have a first prototype here that was not built, and we had a second prototype, the green prototype here. So, well, we gave this all these elements to French flute maker here, and well, instead of discussing it anymore, I'm going to show it to you, to play it. So this is the instrument. Well, I don't know if you can see the conical shape here, and I'm just going to try and play a few notes here. Well, it's not a flute tune, it's an oboe by Schumann, probably. Try. Yes. Yeah. Okay, I think that's probably a good place to end the presentation. Thank you very much.